All right. Thank you everyone for coming. Today, Alex Shkolnik will be speaking. And so Alex is an assistant professor at the Department of Statistics and Applied Probability at the University of California at Santa Barbara. He's also a research fellow at the Consortium for Data Analytics in Risk at the University of California at Berkeley. And his research interests include Monte Carlo simulation for stochastic systems, high-dimensional statistics, mathematical finance, and in particular, quantitative financial risk management. So today, he will be speaking about analytic expressions for the solutions to quadratic programs constrained to standard simplex. I think the problem comes from the portfolio optimization. I'm excited to, I look forward to learn about this. So Alex will be happy to answer questions throughout his talk. So please feel free to interrupt if you have any question. So Alex, please go ahead.
Yeah, so thanks very much for the introduction. I hope everyone sees the slides. Let me know if not. So I'll try to watch the chat box, but I think interruptions are welcome. I don't want to call them interruptions. So like again, thanks for having me. Really glad to be here. I know that there was a cancellation, so I hope to fill in the shoes of whoever was giving a talk. Hopefully, this is interesting. This talk is a little bit of an odd one for me to give because I'm not an optimizations expert. This is actually the first time I'm kind of giving this talk, specifically discussing the optimization aspects of the work. Last couple of talks I've mostly focused on portfolio theory, so that's kind of one reason that the talk is odd. This is not really my area, but I really think we've kind of found something new here. The second reason it's odd, it's also on, the talk is on the topic of quadratic programming, and there's this vast literature. It's such an old problem. I guess the only way it could have been worse if this was on linear programming. But like I mentioned, I feel like there is something new here. I kind of got an inkling of the first result in 2016, and then it sort of lay kind of dormant for a couple of years. And I met my student Alex Bernstein, so he's on the title slide. So he's a PhD candidate here at UCSB at the statistics department, and he was coming in with a master's from University of Washington, St. Louis. It was on optimization, so I thought this was a perfect problem for him. And so in the past almost couple of years now, maybe a year and a half or so, we've been working on this. And so, with that, let me kind of get started. So this slide is mostly to set up some notation. Everybody knows what a quadratic program is. I think maybe the only thing to kind of take note of here is I'm going to be using this inner product notation, this angle bracket. And so I'm minimizing a quadratic form. Q is going to be a symmetric positive definite matrix. P is the variable that denotes kind of the dimension of the problem. A is a matrix of linear constraints. I realize that canonical is a bit sort of subjective of a term, but that's kind of what I would call a canonical form for a quadratic program. The particular kind of interesting element of this that I'm going to focus on is this constraint to the positive quadrant. And so every variable of this x, of this p-dimensional vector x, is going to be non-negative. And without this, everyone knows that there's a closed form solution. So if I just crossed out this last line, I single it out from these other linear constraints because with this line present, there appears to be no closed form formulas, but as soon as you cross it out, there is one. And that's basically what this slide is about. And with this additional non-negativity constraint in practice, and for me in practice means we're computing portfolios. For this talk, that's going to be less important. But in practice, a numerical solver must be used. And so I've listed a few that we've experimented with. ADMM I'm going to discuss because that's what we benchmark our code against. If you have other things that we should be looking at, I'd appreciate references if you kind of have whether it's your work or you just know of a paper with a good solver, please just put it in the chat box. I'd love to take a look. Our our goal is going to be maybe a strange one. It's basically to find an analytic expression. I'll say what I mean by an analytic expression, and this terminology is still a little bit up in the air. I'm using the term analytic in a very particular way. The definition here comes actually from Wikipedia, so I'll read it. Um, an analytic expression is a mathematical formula that entails only well-known operations that lend themselves readily to calculation. So that's what I think we have. I think that's a fair statement. So I don't want to go as far as closed form formula, but I do want to say an analytic expression. And the motivation, at least a motivation for me, has been optimized portfolio composition. That sort of comes from my applied work in math finance. And here that's a little bit kind of on the side. The literature on this is obviously really vast. I didn't actually know what to put on this slide, so I decided to limit it to a few things. If you have a particular paper that's kind of one of your favorites in mind, as I said, mention it in the chat box, and we're basically trying to look through as much of the literature as possible, mostly to make sure we haven't reinvented the wheel or reinvented something. That's kind of what we're in the middle of trying to figure out, and we've been working on that for quite a bit. Here I mentioned a couple of papers. So there's this reference to Gould and Toyna. I'm not sure if I'm pronouncing the names correctly, but this is 2000. I think it's actually the most recent version is 2013, and it's essentially a bibliography, a list of all papers on quadratic programming, from the beginning. So it's just hundreds and hundreds of papers there. And our recent kind of focus in terms of writing code has been on ADMM, alternate directions method of multipliers. And so we've been sort of in touch with Stephen Boyd on this. He's here on a couple of these papers. This last one in particular is on this method called OSQP, which we benchmark against. And so there's just no way to cover all the solvers on one slide. So apologies if I haven't sort of covered the one you prefer, but we're certainly going to be experimenting with different solvers in the future. So the rest of the talk is kind of broken down into a number of sections. I'll start with a little bit of background. Mostly this is just to give you a sense of the motivation that we started with, and a little bit of background in history. As I said, we've been kind of pouring through the literature, and that's going to be, some of it is going to be in this background section. I'll then talk about the theory, sort of the current theoretical results we've been able to establish thus far. I'll run you through a couple of numerical results just to show you some of those. I'll then mention kind of current progress. So we're not solving the quadratic program that I've written in this slide in its full generality. We're working towards that slowly. And so this subsection here on progress is going to kind of walk you through kind of where we're stuck, where there are some challenges, and maybe there won't be much progress past this, but hopefully there will be. And in a conclusion, there's a couple of nice things, extra slides in the appendix in terms of a Python implementation of what we have, and so maybe if there's time, I'll cover that. But to get started with the background, so we're speaking of kind of general purpose solvers for quadratic programming. The first one generally that seems to be recognized as the first general purpose solver is the critical line algorithm by Harry Markowitz. That's the founder of modern portfolio theory. So I'm going to call it for short CLA. And this CLA has been largely ignored by the optimization community for a number of reasons. I'll discuss it on the next slide. And the credit for the first general QP algorithm typically goes to, or usually goes to Philip Wolff. This is the 1959 paper on the simplex method. So essentially adapting the simplex method for quadratic programming. There's a really interesting summary of all this background and history in the really nice paper by Cotto and Infinger, both from Stanford in 2010. So they discuss, part of this paper, they discussed a lot of the history of Markowitz's CLA, talk about the possible reasons why it's been ignored. So I'll read a few kind of quotations I thought that were interesting. So Markowitz's 56 paper can be said to have a number of qualities that discourage readership. I think anyone who's read Markowitz can attest to that. The term quadratic programming appears only twice, abstract in the 17th footnote. I checked that. That's true. The paper's notation presents stylistic challenges. And in 1959, Markowitz did write a clearer version, but this was part of a book. So the book was called Portfolio Selection. And so the book title itself, it kind of leads to one to suspect that the book would have failed to attract the right, not the right readership, but the readership of those who are actually focused on developing quadratic programming solvers. The second part of that paper actually goes on to prove that the CLA and the Wolf-Simplex method are equivalent. So in other words, the iterates that they produce are, there's a one-to-one relationship between them, even though the two methods at kind of first glance look very different. A lot of different anecdotes in that paper. One of the kind of interesting ones is where Cottle mentions that Philip in the personal communication acknowledged that without Markowitz's paper, my paper on the simplex method for quadratic programming would not have been written. So I find this quote fairly appropriate in that we kind of have we're in some sense in a similar position. So our inspiration is also from a paper in finance. So it's this paper by Clark, De Silva, Thorley. So if I do anything today, I hope to kind of get it across kind of your attention if you're not aware of it. I was not aware of it. I was forced to read it back in 2016 by my colleague Lisa Goldberg at Berkeley. So we would meet sort of very frequently, and she just kept telling me to read this paper, and I would just kind of bristle at the suggestion because I found the mathematics in it not very appealing. But it was definitely proven to be wrong. There's a really interesting result there, I think, and I think it's new, and perhaps not. I'd love to hear feedback on this. And at least I believe it's reasonable to suspect that this paper would not make it into out to an optimization audience because it's in the Journal of Portfolio Management, and that's mostly they have excellent papers, by the way, but mostly geared towards a financial practitioner readership. There's no proof is maybe a little bit harsh. There is a proof in the appendix. I can't follow it honestly. It feels to me like the authors just have really great financial intuition that I don't have necessarily, and they were able to basically I don't want to say guess, but state the formula, and it's mostly correct. It's not entirely correct. It doesn't, there's some glitches with it. I can show you sort of what I mean, but for all intents and purposes, it's a really interesting result, and that's basically where I want to start off with here. So this is the setup of the result, right? Setup of Clark, De Silva, Thorley. What they begin with is, they call it a single index model. It's basically we're going to start off with a matrix, P by P matrix that is a diagonal matrix. So we'll focus on this delta term. This is just a diagonal invertible matrix. The diagonal entries are delta 1 squared to delta P squared. And you're going to perturb it by this rank 1 structure. So beta is a vector. There's an outer product here. Sigma is a number. And so all we're doing is we're taking a diagonal matrix and perturbing it by, giving it a rank 1 update. And this is an important model in finance. So we'll set that aside as to why this goes back to the capital asset pricing model in finance. And then they consider this minimization. So this would be computing what's called the minimum variance portfolio, subject to no short sales. So you're minimizing, the objective here is the variance of your portfolio, the risk of the portfolio. You're doing this subject to a fully invested constraint, and you're doing it without short sales. So you're only buying securities, not selling. And that's where kind of the closed form solution is stops. It's without this constraint, you get a closed form solution. With it, it's generally believed that you don't. And here's the formula of Clark. So we've kind of cleaned up the theorem, given it a rigorous proof. That was sort of our first warm-up exercise that took quite a while. We had a number of mistakes that finally slowly got cleaned up, and we got better and better proving a result of the sort. I'll walk through sort of a more general proof just to give you a sense about how this was done. But first, let me walk you through the result. So again, the model here, the matrix Q is a diagonal plus a rank 1 update. We're going to be solving this quadratic program in equation 1. And the solution just is kind of broken up into 3 parts. First of all, there's the minimizer, which is just, it's taken a solution that I would call the unnormalized minimizer W. So I'm going to really direct your attention to W in a second. But here, once you have W, you just normalize. So this division here just ensures this constraint holds, and that's it. So X, there's nothing tricky about about X. All of the content is really in this W and later on in this map psi that I'm going to discuss. So these are normalized weights. It's a difference between E. E is a vector of all ones. That's, you sum up all the, portfolio weights in here. That's the fully invested part. You can think of E as an arbitrary vector in a positive quadrant, really. There's no harm in that. But for now, E is a vector of all ones. So it's a difference between E and beta, which comes from this rank 1 update, and some number theta. So here I'm going to be putting a positive, right, operator positive part. So I'm essentially going through the entries of this vector, this difference, and just zeroing out the negative components, zeroing out the negative positions in the portfolio. And then I reweight everything with the inverse of the, of this diagonal matrix. So what's this theta? This is going to be the non-closed part of it. This is sort of a closed form formula as long as you know theta. And theta is a number which is going to be implicitly given, and more precisely, it's going to be a fixed point of a particular mapping, and that's this mapping psi. I'll show you what this looks like, I think, on the next slide. But just to get a sense of it, it's operating over elements of this beta vector and the delta matrix, and the argument to it, which is a number. So I have the argument I'm going to call var theta, whereas theta is the fixed point of the map psi. So you plug into the solution, it's the fixed point that you plug in, and this map is defined otherwise on the on the reals. And the argument here is basically dictating how many terms are in the sum. Right, so that there's nowhere else does the argument appear but in the summing condition. So I'm going to exclude certain terms and include others. I have a comparison here. I don't know if I'll very quickly do this. This is a comparison to the actual formula that appeared in Clark. So this is it. This is a very similar slide, but they have sort of, first of all, they took the function to be kind of the inverse of itself. So you could potentially get a division of 0. That was not nice, but not too harmful. And then the summing condition was a little bit off. So as long as you have a lot of negative entries in this beta here, there was actually going to be you're not going to solve it correctly. So, just sort of for being completely transparent, this was the formula in Clark, and it doesn't completely work, which is why I'm not stating it as a theorem here. So we're back up to here where I'm going to be using the fixed point theta to characterize the solution, and we've been able to establish a proof of this. So this map psi, this is what it looks like. It's a step function. I'll dig more into kind of some of the properties here. For now, all I'll say is it's a step function. The fixed point does turn out to be at the maximizer of it. That's realized this recently, even though it's not too important. But this is what it means to be a fixed point. You have an identity, and whenever the function crosses the identity, that's the fixed point, and that's what's used to characterize the solution of this simple quadratic optimization. I just noticed there's somebody mowing the lawn. I hope my audio is coming through okay. Let me know if I need to speak up. There's a little bit of noise in the background here. So what the computation of the solution is fairly straightforward. You input not the matrix, but the components of the matrix. So you input the beta, the delta, the sigma. You compute the fixed point. I'll discuss how we do this later on. And in here, in one dimension, you can almost do a brute force type of a search. You have there are p-values of this function, so you could basically just enumerate them. You can use a greedy algorithm. I'll end up talking about fixed point iterations. And so however you compute it, you form the unnormalized minimizer W. That's this expression with a difference and the positive part of every entry. It should remind one of a greedy algorithm. And that's actually kind of the intuition for the original quote unquote proof in Clark. It's you're excluding essentially those entries where this vector beta exceeds a certain threshold. And that's kind of the intuition from finance. You're excluding risky stocks. And then you return the normalization. That's the one that gets you the fully invested constraint, and that's the final minimizer. So our starting point is, how do we extend this? Can we extend it? What are the extensions that are worthwhile to pursue? I'll give you one that's kind of almost immediate. You can replace that vector E by any vector V in the positive quadrant. you can even generalize this a little bit further, but once you stay away from the positive quadrant, you may not even have a solution. So that's why I put it this way. And nothing changes. Well, I shouldn't say nothing changes. The normalization changes. The E gets replaced by this V. But the structure of the solution is the same, and the map psi gets a little bit updated. There's entries of V entering into the numerator, and they also now appear in the condition for the summand. So now I'm at the theory portion. This is where we're going to try to push these extensions further, and I'll show you sort of the direction in which we go in. We're interested in all sorts of generalizations, but one thing, kind of the obvious one is to say, what other matrices Q can we do this for? And can we add other constraints? And we believe we've kind of done a good job on this first part. And the second part, we're having some issues. I'll show you some. This is the kind of in progress part with some challenges, hopefully to be resolved soon. And the goals are, twofold. Again, one is analytic expressions, and these are, from a portfolio standpoint, they give you insight into the composition of a portfolio. And the second goal is fast algorithms for quadratic programming, and they go kind of hand in hand. Once you have an analytic expression, you can start designing sort of a clever and fast way to compute this thing. In terms of the starting point for this generalization, and the one I'm going to discuss is this one, the one where we generalize the matrix Q, we're going to be thinking of factor modeling and what kind of matrices arise out of factor models. So factor model is, kind of goes hand in hand with PCA. So a lot of models are written as a low dimensional structure plus kind of a residual variable. So this is, some response variable y that's linear, that's the linear model part, and some residual z. And the standard assumption of factor models is that the predictor variable and the residuals are uncorrelated. And that leads you to the following factor structure for the matrix Q. So we have a low rank component. So in applications of principal component analysis, this would be the principal components would go here, and here would go the estimated residuals. And so again, this is a diagonal matrix, and this would be a matrix of rank Q. So B is P by Q. Therefore, this outer product here is a rank Q matrix. So Q is symmetric and positive definite. That's going to be the kind of just a direct outcome of some of the assumptions of the factor model, and that's the case that I'm dealing with here. I'm not going to have much to say about negative definite matrices. Maybe at some point in the future that would be interesting. That's the NP hard problem. So I don't know if that's on the horizon for us or not, but hopefully. And here's kind of our first sort of, we're getting closer to the result. This is the quadratic program that we're considering. We're minimizing this quadratic form subject to one linear constraint and this non-negativity constraint, right? Every variable is non-negative. And our first kind of useful tool for this is this map phi. And so I call the previous map psi. This one I'm going to call phi. It's quite a bit different. I'll talk about an analog of the map psi that I showed you earlier that was discontinuous. This mapping is in fact continuous. It's easy to verify, and it's built up from the from the primitives of the model. Right? So B, V, and delta, they all enter into this map phi that I've just defined. And here's the first theorem. That shouldn't be surprising given what we've seen before. Again, we sort of ignore this part. This is the final minimizer that's just being normalized. And this is sort of what I would call the unnormalized minimizer that reveals the sort of the geometry of the solution. You can talk, if you're interested, a little bit about sort of the intuition of this from the finance perspective. What is the geometric structure that's kind of being formed? What is it telling us? So I can talk about that if you like, but for now, I'll leave it at this sort of just at this level of description. And theta there it is. So theta is now going to be an element of our Q. So it's a vector. So it lives in sort of the low dimensional space. Q is, you don't necessarily have to think about Q as being much lower than P. There's nothing in the mathematics that says you shouldn't, but that's sort of what the typical setup is. You have a low dimensional structure defining your, kind of characterizing your matrix Q here. And that's what this Q is. So theta now, this fixed point, is an element of our Q, and it's a fixed point of phi, which means it satisfies this implicit equation. So that's sort of our first result, and is a number of kind of interesting side extensions and fixed point characterizations. I'll mention a few of them. So one thing that we've realized after proving the theorem is that these unnormalized weights that I've highlighted, it's to get a solution, you just normalize these. These weights themselves are can actually be characterized as fixed points of a different mapping. So I call this big phi. So this is a mapping in the high dimensional space. This is the dimension, the problem dimension p, the one that's much larger than q. And so, this W is actually a fixed point of this mapping here. Um, Not much to say here other than, it's interesting, maybe not surprising, given that there's already a fixed point characterization in the low dimensional space. There maybe should be one in the high dimension space. And then all sorts of other fixed point characterizations come from this. Here, kind of try to summarize some of these results in a table. So there are two columns to focus on. One is the right-hand column is the problem that I've been dealing with so far. So minimization of the quadratic form on the standard simplex. So this is the constraint that all the entries sum to 1, and we're in the positive quadrant. And on this side, I've dropped that. So this problem has a well-known closed form formula. And what we've done here is, instead of just writing that formula, we've written things in a way that's analogous to the right-hand side. So these quantities you're already familiar with, coming from theorem 1, the normalized minimizer, the unnormalized minimizer. This is that fixed point mapping phi, and the definition of theta as its fixed point. This is the characterization through the fixed point in the high dimensional space p through this mapping big phi. And on the left hand side, I have analogous expressions. You'll see the missing part is this. The only thing that's different here, this is maybe surprising. It was surprising to me anyway, that this positive part operator is missing. As soon as you drop it, you get the same type of fixed point characterizations for this problem, which already has a well-known closed form solution. So these are just some interesting side results, not the main content of the talk. So let me continue with kind of this theorem and give you a little bit of a sense of what's involved in proving this. Kind of what's different. There's going to be kind of one ingredient that's maybe a couple of ingredients that are a little bit different than what one would suspect. So I'll cover the proof, and then later we'll get to the computation of theta. I haven't discussed that at all. How do we actually get this, get a numerical value for theta? So the proof is 3 parts. This is kind of a sketch. The first thing to try is an obvious change of variables. We want positive entries, so let's just have this change of variables here that's going to constrain us to the positive quadrant. So x equals y squared, and I'm going to call y squared as the vector y with all the entries squared. That's all this notation means. And after this change of variables, the original optimization is written very cleanly. Just the length of the vector y is going to be 1. And all the variables are automatically non-negative because they're squared, and we're still minimizing the original quadratic form. And then you proceed to, as usual, write down the Lagrangian and formulate the KKT. So nothing really special so far. Here's where kind of the trick is. I'll try to walk this through. I don't know how much sense I'm going to make here, but at least hopefully it'll get you to kind of see where there's maybe something different at work here. So one thing that we do is we suppose in the proof ahead of time that we know the 0 entries or the positive, the strictly positive entries, and we kind of use this in the proof to build up the final solution. And what's the reason for doing this is because we're going to establish, and this is kind of the key component of a proof. It's actually in a proposition, a separate proposition in the paper that's in preparation. The idea is to take this matrix Q and to write out this low rank component in terms of not the original matrix B, but in terms of this matrix gamma. And so gamma is going to have columns little gamma. And what we're essentially doing is coming up with a basis for gamma that orthogonal cases. I shouldn't say orthogonal. That's not strictly correct. Now, we're going to be trying to kind of preserve this quote unquote orthogonality. The reason I say quote unquote is because this is not really an inner product. It's called a Hermitian form. And it's based on this weighted matrix omega, which actually has 0 entries. That's the reason why this is not truly an inner product. But roughly what's going on here is that we're rotating the columns in a way to preserve this kind of quasi-orthogonality feature and this also positive orientation with respect to one of the constraints. And all of this is done, what's the purpose of doing all these transformations is to establish the sign of the Lagrange multiplier. And once you have a sign of the Lagrange multiplier, essentially you can pull it out of a positive part. That's kind of the only tricky part in the proof. Without this step, when you don't know the sign, it becomes difficult to proceed. And then the final proof is sort of wrapped up in first establishing this mapping var phi gamma in this under this coordinate transformation, and then you transform back to the original coordinates, and that's what gives you this final mapping, the fixed point of which is going to be involved in actually specifying the solution precisely. That's hopefully gives you a little bit of a picture of what's going on. There's very standard things with the exception of this kind of transformation trick and this orthogonalization trick that we've used. And then now comes the computation. So again, the input now is not the matrix Q, but the components, the primitives that are used to assemble it. And then we have to find out this fixed point some way. So I'm getting to the part where I'm going to discuss the computation of this fixed point theta. I've been in the last talk, somebody suggested, well, why don't you just, kind of use another optimizer to optimize over a Q-dimensional space? So you could potentially, subtract off var theta from var phi, square it, basically, essentially square it and minimize that to find the theta. And I think that's a very valid procedure. I'm sure there's a lot of kind of things you could do to try to extract the fixed point of this mapping. Our goal is to try to get analytic expressions, and we thought sort of this kind of a more fixed point iteration approach would be the one that we wanted to pursue, and that's the one I'm going to focus on in the next few slides. And the rest of the steps to return the solution are easy. This is the kind of the closed form part of the formula that you put together for the unnormalized minimizer, and then you normalize and return the final answer. So the bulk of the only part of the non-trivial part, the only non-closed form part is this theta that lives in RQ. And now I'll talk about kind of how we go about computing it, even though there are probably plenty of ways and maybe even a better way than what we have currently. The first thing we thought about is, well, why don't we do a fixed point iteration? You have a fixed point problem. Let's just apply this mapping of phi over and over. And what you'll find is that this thing is not a contraction. It's continuous, but not a contraction. This is what it kind of looks like. This is what it would look like if Q, the low rank dimension is equal to 1. So it's, it has a very high gradient, and this is basically what it looks like. And so these iterates, you start off with 1, and then eventually kind of spiral out. And I don't think we found even one setting for the problem where this thing would converge. It just so in general, this thing is not a contraction, and therefore not suitable for fixed point iteration. This mapping phi. So what we do now is try to bring us closer to the original Clark de Silva Thorley paper, who had a discontinuous mapping. This is what we searched for after that, and here's what we find. We're going to define a mapping psi. So this is going to be the Q-dimensional analog of the Clark de Silva Thorley one-dimensional mapping that I showed you with all the awkward sums, the little awkward step function. And what it entails is solving. It's a solution of a Q by Q linear system. So there's a matrix C, which is Q by Q. There's a vector B, which we're going to form. And that's given any argument at which I want to evaluate psi at. So I have an argument var phi that I want to evaluate psi at. And I use this to form this system. So C and B here actually do depend on var phi. I'll walk you very quickly through it. First, you form this indicator vector. This is roughly it's kind of saying, well, you have a guess at what the solution is, let's take that guess and convert it into an indicator of whether the minimizer has a positive entry or a zero entry. That's what this is doing. And then from this vector chi, which is 0, 1, you form this matrix C and B from the primitives of the model. So these are all the things, the V, the B, the delta, they went into forming the matrix Q. And you have a lemma from this. This is just an algebraic manipulation, nothing fancy going on here. It's just rearranging of terms. And what you can prove is that phi and psi share the same fixed point. They're not the same map. They're very different functions, but they not seem to, but they provably are coinciding in terms of their fixed points. So if you have a fixed point of one, you automatically have a fixed point of the other. And again, the two mappings are very different. Phi is continuous. Here, I wrote it again here at the bottom of the slide. And psi is going to be discontinuous. I'll try to give you some intuition and pictures in a second. But you can kind of see that the 0, 1, this thresholding here that we do is what leads to all the discontinuities. Here's the connection to the original psi map of Clark de Silva-Thorley. I wrote it out again on top. Right, so this is what the original paper proposed after some fixes that we've added on. And the connection, so how do we see the connection between the two? You see that the denominator here is basically the inverse of the matrix C. So if I pull this denominator over, that's what C is. You can kind of see almost the connection. V inverse is the 1 over sigma squared. And this portion right here is this quadratic product here is basically a sum of over these guys. And, so C inverse is basically the inverse of this, the denominator here. That's what it corresponds to. So if I bring the C over to the other side, I'll get something that basically looks exactly like this, but in dimension Q. And so this result took us a long time. We had a number of mistakes. I think they're all been hopefully addressed. This was a really difficult proof to get through. And what it states is that the iterates, the iterates produced by the fixed point iterations of the map psi converge. And we're for now going to say provided that the starting point is 0. I think this is a needless assumption. We used to use it, but I think this could be dropped. Or trying to kind of work on this part. I think any starting point will lead to convergence here. Although I can't say that with certainty, so I'm still leaving this statement intact. And the proof is complicated. I won't go over it. We first started trying to prove it in the one-dimensional case. So Q equals 1. This is back to the Clark de Silva-Thorley model. This was like 3 pages of arguments that were, I'm sure there's some much heavy machinery out there that one can use. Here's the oops. I'll show you. Maybe I'll skip ahead a little bit to the pictures. So this picture is particular. This is sort of how the map with the fixed point iterations would converge in one dimension. You started at 0, which is what we do, but I feel like you don't. I'm pretty sure you don't have to. And you basically climb up this ladder until you hit the fixed point. And this is basically the only way, the one way that this happens. This is what always happens, and this is just due to the properties of this. This funny mapping psi here. Let's see, what did I miss to come back here? And this proof works. This is, of course, in the Q-dimensional version of it. So the proof starts out with first trying to prove in Q equals 1 and then trying to apply it along each coordinate, although it's not, that's not fair. There's sort of some number of other steps involved here. And I think we're finally kind of happy with how the proof goes, but it's having trouble going to have trouble describing it, so I'll skip it. That this feature of psi being discontinuous has been sort of puzzling to us. It almost seems to add robustness to the iterations. So the number of values that the psi makes is finite, and so it's a little bit counterintuitive. You get rid of all continuity, and what you have is this kind of combinatoric flavor to the problem, and it also gives robustness in the sense that you don't need to set any tolerances. You just converge literally until this iterate and this one are equal. So until you're on this plank here, and of course you have to picture this in Q dimensions. And then in terms of the proof in one dimension, what you basically do is it just so far the way we've done it is just to cobble these arguments by contradiction. You start out on this plank and you say, okay, suppose I jump down below, let's try to reach a contradiction. And that's how we do it. We basically show that this map psi always increases up to crossing this line. In this case, the cycling case and the case where this line just goes through, passes through without hitting any fixed point, never happens. This is what always happens. When I say up to sign, it basically is this case or reflected over to the other side where the fixed point is negative. It's just so one and two are the same. And this is what we call the fast fixed point method, FFP. So here's how it works. We get this computation of this fixed point here, and this is done just by iterating this until until the two match, and you don't need any tolerances just because it's almost strange in the code to put this equality, but that's literally what we did. But that's just the nature of this step function property of the map psi, that you can literally go until you're exactly at the plank that you want to be at, and then you form the normalized minimizer, and then rescale it to return the final answer. Let's see. I have a little bit of a detour here into the appendix. This is literally what the code looks like. So this is the mapping psi. This is its definition again. And here is its implementation in Python in 3 lines. You can condense it into even less lines. You can kind of see that, we form the matrix C, the B, and then we issue a solve to the system. And there's no doubt better ways to do this. There should be an algorithm here that would update the solution along each fixed point iteration. That would be more effective computationally speaking. And here are the fixed point iterations. You go until S and T are sort of your fixed point iterates, and you go until that they're while they're not equal, you continue, and you just keep iterating the map. And this is the final answer to the problem. This is the W vector, and then you just realize it's return its normalized form. So I'm going to come back to that slide where I covered the algorithm. So this is the first sort of result that we have, the one that we're writing the paper around, and I'll mention sort of some extensions that we're also working on in a minute. I think I have 15, maybe 10 minutes left, so this looks like enough time. So the next section is on numerics, and we've been playing around with different solvers. This is the one that we started with, so this is the result that I have. It's a method called OSQP. It's based on the method of alternating direction, ADMM, alternating direction method of multipliers. And this is a big sort of effort between Zurich, Oxford, Stanford, several groups involved in developing the solver. There's a paper they have out from last year. And so they kind of say that it beats most available. This is a quote from their website. You're welcome to visit it. So it beats most available commercial and academic solvers. And they have this plot on that website. And this is what we benchmark against. So first of all, it's based on, like I mentioned, ADMM. I'll skip through this a little bit just because I'm running a little bit short on time. But if you're, one reason that we've chosen this is that we saw in ADMM this operation, which we thought could be linked to the FFP algorithm with this thresholding. It doesn't seem to be a very clear connection between the iterates. We're still exploring this and connection to log barrier methods and so on. But roughly speaking, this ADMM is solving this linear system, this augmented linear system, and you can do this in Q. I should have put P times Q cubed, sorry, or Q squared times Q plus P Q squared time. So you can use Woodbury's identity to exploit the fact that this is this has factor structure. So you're not kind of solving the system without any information. And that's what we do in this experiment here. We're basically taking this general purpose solver, but we're giving it knowledge of the fact that there's factor structure. So we're not passing to it the matrix Q. We're giving it the actual components, the V, the matrix B, and the delta. We're feeding all that to it. And the kind of complexity of this I mentioned is, I think it's Q cubed plus Q squared times P. And we're comparing it to the fast fixed point method, the one that I presented here. And so you have the runtime in seconds. These are averages of runtimes over many, many different problem instances. And we're trying to get we tried to get, I'm pretty sure we got two precise significant digits. At least that's what I'm told. We got two precise significant digits with 99% confidence here. And this is the ratio of the runtime. So in other words, this is how much faster FFP was than OSQP. Of course, keep in mind that OSQP is a general purpose quadratic programming solver. FFP is just solving this special instance. But the hope is that we can kind of push this further in generality. Another direction that we're working on, I was hoping to present some of these experiments today, is computing sensitivities. In other words, what are the derivatives of the minimizer with respect to the problem parameters? So the problem parameters were B delta V. They're the ones that composing the matrix Q. Can you actually compute these derivatives? And that turns out to be, there turns out to be, first of all, analytic expressions for these derivatives, and also then therefore these fast fixed point algorithms, and that's just using the chain rule. So in other words, this derivative is, first you take a derivative with respect to the fixed point, and then you differentiate the fixed point with respect to the parameter, and now you have a new expression. They get a little bit long, so I've written a few examples here. This is for the rank 1 model, so diagonal plus rank 1 model. You can kind of see what they look like. So these are derivatives of the fixed point with respect to the problem parameters, and you get these expressions, and as long as you know how to compute the fixed point, you get all the derivatives out. I was hoping to have a table for you today. It looks like we're not going to make it. We were waiting. I was waiting up until 9 a.m. or I guess 11 for you to get a table in, but couldn't do it. I know there is some kind of clever way of computing derivatives with these numerical solvers. I'm not aware of the details. My student is working on it, and hopefully in the next version and in the paper we can include this. But presumably we'd get even better better performance than we did here. Although I can't claim that yet. So progress. As I'm winding down here in the last 5 minutes, I want to mention some progress in extensions. So we've been motivated by the Markowitz problem. This is based on the portfolio theory applications. And so what we're doing is adding just one more constraint. So this is an extra additional constraint, which is basically saying, I want a target return mu for my portfolio. I want to minimize the risk. I want to have a fully invested constraint, and I'm only buying, not selling. The map phi that I showed you becomes more complicated, but still manageable. It's now augmented. So this mapping used to be Q to Q or Q to RQ. It's now we're adding one more dimension to account for this constraint. That may actually be not the right way to go. We're rethinking this whole part. We're actually thinking of maybe better to put this as a linear term in the objective and try to go back to a Q to Q map. Not sure. This is the theorem that we have. We have a couple of assumptions now. One is we assume that it's a binding constraint, which actually I think it is anyway. At least in the useful cases, it is binding. Sorry, in the useful cases, binding. And you have sort of, again, this appearance of a familiar sort of structure for the portfolio, or for the what I call the unnormalized minimizer. So something very similar, but the constraint obviously enters in. And this theta here and this rho are now a fixed point of this phi map. And again, these iterates diverge. And again, we start searching for this map psi. And it looks like this. At least this is our current sort of attempt at it. You kind of hopefully see that the connections between what it was before is just adding an extra row and incorporating this extra constraint alpha. And in practice, these iterates converge. We actually thought we were done and ready, and all we need to do is just prove this, because we had convergence, and we finally found some examples where it's not converging to the right thing. There is one other fixed point. I think I mentioned this in the theorem even. There are two fixed points to this problem, and so there's the right one and the wrong one, and we know what the wrong one is, and this is what we're trying to deal with. In the context of portfolios, what's basically happening is that the wrong solution, the portfolio is loading up on one stock. So it's basically saying buy this stock and stock only, and that's clearly the wrong way to go. And we're thinking about how to resolve this. So that's kind of the update on progress, or where we are now. Hopefully we resolve these issues, and I'll try to get to a conclusion right now. So uh, what we've so far been able to develop are these analytic expressions, analytic in the sense that I've already defined, for quadratic programs constrained to a simplex, so minimizing a quadratic form on a standard simplex or a weighted simplex. And the analytic expressions are in general available for any positive definite symmetric Q. You can always write it in that form that I've shown. However, fast algorithms will be available only when that little dimension Q is much smaller than P. That's the only way we get uh, it's the only way we get a fast algorithm from the analytic expression. Not to say that analytic expression is not useful; it's useful for applications anyway. But only do we get fast algorithms only in the case when we have this kind of low dimensional factor structure. And so I've already showed you some results on the Markowitz problem that are still work in progress. We're hoping to fix some of these issues with multiple fixed points that have come up, unfortunately. And after this, the goal is to see how far can we go. Can we get to this general, to a general QP solver, or at least part of the way there. I'll wrap up here, and I'll ask questions. I think 5 minutes to go, so I've made it on time. Here's my email. We'll try to get the draft out, hopefully by the end of this month, although I keep saying this every week and it's still not coming out, but hopefully by the end of this month, we have something posted and out there, and we'll welcome to share it. And if you have questions, you can shoot me an email, and I'll certainly answer your questions now. I apologize for the noise. There's just with Zoom, unfortunately, there's no way to control somebody mowing the lawn next to you. So I apologize if there's noise coming in.
Hello, I have a question about the very beginning before we get to solving the problem.
Yes.
Because not being in finance, are people really interested in that very simple Markowitz problem without transaction costs or other things? Is it useful to have that simple QP?
Yeah, I'm going to get to that slide. Yep, this one. Yep. I'm not a practitioner. I've talked to a lot of them. I've actually sent out some of this work to the optimizer group at MSCI Bara. The short answer is no, but with a couple of caveats. So first of all, even in practice, you're first of all dealing with data, and so estimating accurately this vector alpha is already kind of a non-starter. So in many ways, even adding this constraint is maybe questionable. In practice, you have all sorts of other constraints, and I'll tell you sort of how to get to the first immediate kind of practically useful version of this would be to actually incorporate upper and lower bounds constraint on the sex, which I think we're close to doing. This would be the first thing that I could actually go to somebody in the financial industry and say, look, we can actually use this because of speed. We run maybe. Suppose we have, our portfolio team is working on maybe stress tests, and we need to run tons of these Monte Carlo simulations, and understand sort of what happens in such and such a scenario. The first practical use case would actually maybe not even we could even maybe cross this out, but put upper and lower bounds on this. The biggest concern that comes with noisy data is the fact that this optimization problem is in fact producing extreme weights. This is sometimes been called the Markowitz enigma, the fact that you get pretty junk out of it. When you put a noisy perturbation to this matrix Q that comes out of data, you get essentially these portfolios that have extreme weights that are non-investable. And so the first practical use case would be to actually even drop this, even though you could add it, but have upper and lower bounds on the position so you don't get these extreme weights. That would be the first useful case for us, and that's the one we're kind of going towards in terms of practical application. In addition, other constraints that you put in, transaction cost is certainly one direction to go. We haven't thought in this direction, but yeah, practitioners care about this. Another thing that they care about is factor tilts. So you're looking to track some ETF, and so you would put a constraint here that could try to you have some index and you're trying to kind of remain close to it, so some measure of a distance between the solution in some vector. So that would be another practically useful thing to put in. But from my speaking, I don't work in the industry, but I certainly speak to a number of people who kind of practice this stuff. It's a lot of emphasis has been placed on exploratory analyses, and there it's okay to sacrifice some of the realism. So you're basically trying to communicate to your clients, in such and such an event, and we're now finding ourselves in this very uncertain world with a pandemic, fires, climate change, and so on. You want to be able to communicate to your clients, how do these portfolios react to these different scenarios. And so for that purpose, it's okay to be sort of more on a kind of stylistic type of a description. But you're right, in practice, transaction costs are important. I would say there's a paper by Stephen Boyd. This was work funded by BlackRock. They've been working on this stuff, and actually BlackRock recently bought a company of my colleague Lisa Goldberg to handle these issues. So they're working on transaction costs and tax implications and all sorts of things. So yeah, I don't mean to claim that this is anywhere close to practice. And the first kind of immediate goal would be to get to upper and lower bounds on X. Hopefully that answers your question.
Yes, thank you.
Mhm.
Right. Thank you, Alex. If there's, I actually have a question. So,
Mhm.
So one of the key steps is the equivalence of the fixed point equation for phi and psi, right?
Right here. Yep.
So
That's right.
that does it how is this like very specific to this context, or
Yeah, it's not difficult. Here's the proof roughly goes like this. Let's say start out with one of them, this one right here. If you start out with this one, and now let's say we're at the fixed point, which means I get to replace the left-hand side with theta, and I get to replace this var theta with theta. And then you just rearrange the terms. So essentially it's just breaking this this side apart, and that's why this chi indicator is needed. So this chi is involved in getting rid of this positive part here, and now one term goes on the other side, the other term goes on the other, and then you basically arrive at this system. There's nothing tricky there. I mean, I shouldn't say there's tricky. There's always puzzling, and I kind of just often catch myself kind of getting stumped as to, well, how is this actually all working? But yeah, you do get this continuous map and this discontinuous map, and they match exactly at the fixed point, but they're very different. What this really suggests is that there's probably many other maps that you could form and play around with, and their fixed point properties, convergence properties, could be different. Basically there, infinite many ways to kind of rearrange this, equation to get something that looks like a fixed point equation, and then try to run fixed point iterations on it. And here I've shown you two. One is phi, which has this. Oh, hold on. One is phi, which is continuous, which is nice, but it's not a contraction, so it gives you, these iterated spiral out of control. And the other one is the psi, which magically gets this, has these nice properties, and at least, in one dimension I can picture it.
so so this particular property that you are guaranteed to have the fixed solution for this fixed point equation, is this something again? Is this something that can be used for other purposes?
I don't know. Yeah, I don't know. It's a lot of I think we're kind of hoping to find out that this is new. We're basically looking to see if we've reinvented something, and then after that, we're going to ask exactly the questions that you're asking. What else can we use this for? There seems to be this connection between fixed points and quadratic programs. What it all means, I honestly I don't know. I'm just so far kind of puzzled with the results that we do have. I'm puzzled with the fact that this picture is basically representing the one way that this fixed point could happen. I didn't expect that to occur. And so lots of puzzles. Yeah, I don't have any answers. But yeah, hopefully, this table that I shown you is kind of a first attempt at trying to summarize sort of fixed points and quadratic programs and what are some of the connections. I couldn't begin to tell you what it all means, and we're kind of slowly so I mean, so far it's just me and my student Alex, and we're hoping to kind of grow the group, and once we have this first paper out, we'll hopefully try to attract some graduate students. I'm in the stats department, so there is interest in optimization, but it's all for like deep learning and stuff, and so it's been difficult to kind of attract students to this. Although I'm kind of hopefully kind of trying to form a little bit of a group around it, contacting some folks at Stanford, and hopefully this takes off. I know very little, and I've just working through this, I've realized how limited sort of my abilities are. I mean, this kind of the proofs here have sort of pushed me to the limit in terms of thinking. It just took months to get this even basic result out. This one, which one? The one with the this picture, just to prove that the fixed point is unique and you get convergence. It just took forever. Now it's sort of kind of sinking in and it's obvious. But yeah, so in summary, we need help. So if anyone wants to help, I'll certainly, once the paper comes out, I'll send along, and it would be exciting to kind of to push this forward. And even if it does turn out to be that this is a reinvention of something, so far that doesn't appear to be the case, but we'll see.
Very cool. So, all right. Thank you very much. Does anyone have anyone else have more questions? So yeah, then otherwise I will stop recording.